Radioactive decay is the random and spontaneous process by which a nucleus of an unstable atom loses energy by emitting radiation. There are three types of radiation which can be emitted: alpha particle, beta particle, or a gamma ray. Binding energy is the energy that would be required to separate the nucleus of an atom into its constituents. A graph can be drawn to represent how average binding energy per nucleon varies as the atomic number, which is the number of nucleons, increases. The greater the binding energy, the more stable the atom. Again, radioactive decay in an atom is random and spontaneous. However, it can be modeled as an exponential decay. A simple experiment with dice can be carried out to demonstrate this curve. In the experiment, 500 dice were rolled, each with a single side colored. The dice that landed with the colored side upwards were removed and recorded. The remaining dice were rolled, and the process is repeated. The experiment continues until eventually there are no more dice. In other words, the atom has fully decayed.
Eventually,
the number of recorded colored dice at each stage are then plotted on the graph. This trend is exponential decay, because the probability for each die to land with the colored side facing up is a sixth. Therefore, as the total number of dice decrease, the chances of having colored faces also decreases. Relating this to radioactive decay, the rate of the number of nuclei decaying decreases over time. Since each die had a constant probability of it landing on a specific side, nuclei have a certain decay constant. The equation for half-life can be derived from this graph. N is the size of radioactive material at a given time. T is time. The graph can be expressed in an equation by including a decay constant, lambda, which is negative. Integrating the equation gives us this expression in terms of the initial size of the radioactive material, which is represented as n subscript 0. Next, write this as the half-life of the radioactive material. To give us the final equation, we have to log both sides and rearrange the equation to make the radioactive half-life time the subject. Our final equation is log 2 over the decay constant, which is lambda.